again from where we had stopped in the last class, that I had introduced two new terms or ideas that we had. That is, one was irradiation and one was radiosity. So just to start again with what was irradiation? Irradiation was the total energy or incident radiation which was incident on the surface. 8 minutes, let me get my pointer. Whatever was coming on the surface was known as irradiation, and whatever was leaving the surface was known as radiosity. So if the amount of radiation incident or coming on a surface, falling on a surface is denoted by the letter G, irradiation was, radiosity was what was leaving the surface. And what was leaving the surface comprised of two parts. One was because of the emission that is going out of the surface because of the temperature of the particular surface, and the second one was the part of the incident radiation which was reflected back. So they had two components to it, epsilon EB plus your reflectivity into the total incident radiation. And based on that, we tried to derive a general relationship to find out what was the net rate of heat transfer between two bodies. And what we found out that when we are trying to do that, there were three terms that we were talking about. One was called the surface resistance of the body 1. Then was the surface resistance of body 1. Then was the space resistance as the energy is being transferred from body 1 to body 2. And the last one was again the surface resistance of body 3. And we had found out the expressions for both surface resistance as well as space resistance. The general expression for surface resistance was that EB minus J, EB is the amount of emission that is coming out of black body, minus J was my radiosity, divided by that was the potential difference between the two. And the resistance was 1 minus epsilon divided by epsilon into A. And the space resistance, the general expression, if this was from the radiosity from the body 1 was known as J1, and that too in body 2 was known as J2, then J1 minus J2 was the potential difference, and the resistance was equal to 1 by A1 F12. So if this whole thing was written in the form of the way we write electrical resistances, then we saw that the two potential differences in the case of the surface resistance of body 1 was EB1 minus J1 divided by the resistance. Next was the space resistance. The potential difference was J1 minus J2 divided by the resistance again. And the last one, which was the surface resistance of body 2, was J2 minus EB2, which were and divided by this particular resistance. So when we are trying to find out what is the net rate of heat transfer between body 1 and body 2, that is EB1 minus EB2, we have to include all the resistances, and these resistances are summed up in the denominator. So this is a general expression we had found out in the last class, and that's where we had stopped. Now, if you remember that when we were talking about trying to find out the net rate of heat transfer between non-black bodies, that means gray bodies, we had talked about two parallel plates, and we had seen that if we consider transmittance to be equal to 0, how the amount of radiation that is falling on one surface is part of it is being absorbed by the surface, rest of it is reflected back. Amongst the portion which is reflected back to the original surface, is part of it is again absorbed, part of it is reflected back, and this reflection and absorption continues forever if it is a case of two parallel plates of infinite size. And we had developed relationships for that. Now this is this relationship that we have developed, that the net rate of heat transfer between two bodies is a general one, and we can find out this for any specific case. So let us see how do we do that. So for radiation heat transfer between two surfaces, the first case we consider is two parallel planes. This we had already done before. We are doing it again now in the case using this general expression. So if I have two parallel planes which are of infinite length, then the areas of the two of them are the same. That means A1 is equal to A2 is equal to the area A. And the view factor, because whatever comes from from plate 1, entire amount of that energy or the radiation falls on plate 2. Plate 2 can see everything because they are of the same size and they are of infinite length. And whatever is coming from plate 2 can be seen entirely by plate 1. So F12 is equal to 1. And similarly, F21 is also equal to 1 if it is required. Now, if I look at the general expression, Q12 is equal to EB1 minus EB2 divided by the first resistance, surface resistance. This is the space resistance, and this is again the surface resistance. Now, if I put these conditions that we have, that A1 is equal to A2 is equal to A. So, jahan pe A1 is there or A2 is there, I just simply put the value of A. I don't differentiate between the different areas. And where we have a value of F12, I put in that F12 is equal to 1. So you see there's a in the denominator of all these cases, which is then multiplied to the top. And EB1 is written as sigma T1 to the power 4, and EB2 is written as sigma T2 to the power 4. So if I take sigma common and A out here, this comes out as T1 to the power 4 minus T2 to the power 4. And if you open up the brackets out here, what do I get? 1 by epsilon 1 minus epsilon 1 by epsilon 1, which becomes equal to 1. If A is taken as common, this becomes equal to plus 1. 1 by epsilon 2 minus epsilon 2 by epsilon 2, that is minus 1. So this plus 1 and this minus 1 cancels out. And what we are left with is sigma A T1 to the power 4 minus T2 to the power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Now, this is what we had already derived. I'll go back and show you where we had derived in case you're thinking about it. This is where we had derived it, if you remember. That is A or A1, sigma T1 to the power 4 minus T2 to the power 4, 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This is for parallel plates. We had done this by doing all this back and forth reflections. But now we can find the same expression from the generalized expression, putting the particular conditions. And we had also seen that for concentric spheres of cylinders of other geometries, Q12 is equal to A1 sigma T1 to the power 4 minus T2 to the power 4 divided by 1 by epsilon 1 plus A1 by A2, 1 by epsilon 2 minus 1. We will try to see how we can get this one from a general expression also. So the general expression is the easiest way to solve the problem. Now, before we go into that, let us still do a little more simplification of this one. That is Q12. So this is when we have two parallel planes which are non-black in nature, then the net rate of heat transfer between the two of them would be, which can be written as sigma into A, T1 to the power 4 minus T2 to the power 4 divided by this epsilon terms at the denominator. If we are writing this expression for a black body, then epsilon 1 is the same as epsilon 2 and their both values are equal to 1. In that case, this simplifies to Q12 is equal to sigma A T1 to the power 4 minus T2 to the power 4. This is something we have seen before. And because they are parallel planes, that means the view factor here also becomes equal to 1. We had derived these expressions before. Now let us look at two concentric infinitely long cylinders. So there are two cylinders like this. This is a cross-sectional view. These are infinitely long cylinders. The outer one has got a radius of R2 and is at a temperature of T2. The inner one has got a radius of R1 and is at a temperature of T1. We want to see how what is the net rate of heat transfer between the two surfaces going from Q12. That is net rate of heat transfer from Q1 to, that is from surface 1 to surface 2. Now, you know, whatever radiation goes out of surface 1, the only direction in which it can go is outwards. And if it can go outwards, nothing is falling on itself. So F11 is equal to 0. And from the summation rule, you know that since there are only two surfaces, F11 and F12 is equal to 1. Or we can say that F12 is equal to 1. That means whatever goes out of radiation that comes out of surface 1, the only place it can go and fall on is surface 2. So the view factor of F12 is equal to 1. So now let us put these values in the general expression. This is my general expression. I'm now putting EB1 equal to sigma T1 to the power 4 and EB2 equal to the sigma T2 to the power 4. What else is there? That A1 stays as A1 because now the areas are different. A1 has got a very different area from A2. We cannot cancel them as a write as A. So this is A1 and this one stays at as A2. And if you open up the brackets, so what we do is that we multiply the numerator and the denominator by A1. If I multiply the numerator by A1, I get sigma T1 to the power 4 minus T2 to the power 4 into A1. And the first term in the denominator only becomes 1 by epsilon 1 minus 1. And this one becomes plus 1 because I have multiplied it by A2. And the last term is 1 minus epsilon 2 by epsilon 2 into A1 by A2. This is, and if I, or these two will get cancelled out, these two plus 1 and minus 1. So this is left with 1 plus epsilon 1 plus 1 by epsilon 2 minus 1. This entire amount is multiplied by A1 by A2. This is the same general expression that I had written earlier, and I had said that for two concentric spheres or two concentric infinitely long cylinders, this is how we can find out the rate of heat transfer. So when we do the trying to find out the rate of heat exchange between bodies, using a general expression is the most convenient way of solving it. Now let us look at that. This is what is called a three-body problem. So three-body problem means that essentially heat is being transferred between three bodies. Now, till now, if you remember, we had only seen this part. That means between two bodies, EB1 and EB2. So what is it? Let me just get my pen and try to show you. So we have, say, a body 1, and here we have a body 2, and we are trying to find out the net rate of radiative heat transfer. So for this, we consider the surface resistance of body 1, which is part here. Then comes the space resistance between body 1 and body 2. And the last one is the surface resistance of body 2. हमने अभी तक इतना ही किया था, only this much. Now we are considering a third body. And usually a third body could be another one out here. This is body number 3. So when we have a third body out here, you see what happens is that this part is the surface resistance. This part is the surface resistance of body number 3. This part is the surface resistance of body number 3. And this is the interaction between body 1 and body 3. And this is the interaction between body 2 and body 3. So there are different kinds of interactions which are there. And this one, this one, this one, and this one, these are all space resistances. And this one, this part, and this one are all surface resistances. This is surface resistance of 1, this is a body 2, and this is a surface resistance of body 3. Now, what happens is that when we have a body where when the heat is being exchanged between body 1 and body 2, the third body that we talk about very often is the room or the surroundings. Suppose these two bodies are placed inside a big room, then this room itself becomes the third body. So if you look at the area of this room, it is much, much larger than the area of body 1 and or body 2. Because if you just imagine that there are two bodies kept inside any room that each of you are sitting in, the area of the room is way larger than the areas of the two bodies. So if I have the area of the room as to be very large, that means this A3 is very large, what will happen? This term becomes very small. That means 1 minus epsilon 3 by epsilon 3 A3, this becomes a very, very small term. And because it becomes a small term, then J3, this resistance now vanishes off. If this resistance vanishes off, J3 becomes equal to the 2EB3. That means what is it that I'm talking about? Because the area is so large that there is hardly any surface resistance of body 3. So this is what is practically seen as the most common situation. But this general expression or figure that I've drawn is for a three-body problem, where when there is heat exchange between three reasonably sized bodies that are there. So in order to understand this, trying to understand this in terms of this electrical analog, let us do a simple problem. So let us see what we have in this problem. There are two parallel plates, 0.5 meter by 1 meter, and they are spaced 0.5 meter apart. So both the plates, this side is 0.5 meters, so this side is also 0.5 meters. The length is 1 meter, each of these plates, and the distance between these plates is 0.5 meter. One plate is maintained at 1000 degrees centigrade, and the other one is at 100 degrees centigrade, 500 degrees centigrade. So the heat transfer will happen from the 1000 to the 500. Let us call this body 1 and let us call this body 2. The emissivities of the plates are 0.2 and 0.5. This epsilon 1 is equal to 0.2 and epsilon 2 is equal to 0.5. These plates are located in a very large room, the walls of which are maintained at 27 degrees centigrade. So these two plates are present in a very large room. The temperature of the walls of that room is 27 degrees centigrade. The plates exchange energy with each other. The plates exchange energy with each other and also with the room. So they exchange energy also with the room, but the plate surface facing each other should be considered for analysis. So when we are talking about the net rate of heat transfer, this is the net rate we are talking about from one plate to another. Find the net heat transfer to each plate and to the room. That how much of heat is being transferred from plate 1 to plate 2 and then from plate 2 to plate 1 and to the room. Now let us look at, so this becomes a three-body problem. The first body is the plate at 1000 degrees centigrade. The second body is the plate at 500 degrees centigrade. And the third body is the room, which is at 27 degrees centigrade. So if I look at this, 8 minutes, let me just blow this up a bit. My figure, so this is my body 1, this is my body 2, and I have the 3 resistances present. Now, as far as body 3 is concerned, if you remember, it is written that the area of the room is very large. So the surface, that means the surface resistance of this large room becomes negligible and J3 becomes equal to EB3. So this is what now my the electrical analog part of it looks like. So now this is what we are going to work with. Now let us see. The temperature of the first one is 1273. I've written it in Kelvin now. Temperature of the second plate is 773 Kelvin and the wall temperature is 300 Kelvin. The distance between them these two is D is equal to 0.5 meters. Now, if you remember those hotel charts that we had talked about, one of those hotel charts, that is the first one that is there, had this kind of a figure where we had 2 parallel plates. Let me just increase the size of this also, slightly more. 2 parallel plates which are of equal size, and the length of this one was L1 and this was equal to L2 and this is D. Now in our case, this L1 is 0.5, L2 is 1 and D is equal to 0.5. So L1 by D, if you look at it, this is 0.5 by 0.5. So L1 by D is equal to 1. And what is the x-axis? X-axis is L2 by D. L2 is equal to 1 and D is equal to 0.5. So 1 divided by 0.5 becomes equal to 2. So if I go from the value of 2, go up straight till I reach a value of 1 out here, and here I go and find out what is the effect, the view factor that is there. The view factor that comes out from here is 0.285. Is 0.285 from this figure. And you know that A1F12 is equal to A2F21 from the reciprocity rule. And since A1 and A2, the areas of the 2 plates are identical, then F21 is the same as F12. That is 0.285. Now let us look at the other things which are there. For example, we see that from the summation rule, F11 plus F12 plus F13 is equal to 1. What is F11 now? F11 means whatever radiation is coming out of body 1, how much of it is falling on itself? Nothing. Whatever comes out of from 1 will either fall on body 2 or it will fall on body 3, which is the walls of the room. So nothing will fall on itself. So F11 becomes equal to 0. So F13 is equal to 1 minus F12. We have already found out the value of F12, and this helps us calculate the value of F13 as 0.715. This is when we are trying to do the summation rule for body 1. Now, if I do the summation rule for body 2, what I get is F21 plus F22 plus F23 is equal to 1. Just like body 1, whatever is coming out of the plate 2 will fall either on plate 1 or on the walls of the room. So F22 is equal to 0. So F23, this is out here, is equal to 1 minus F21 because F22 is equal to 0. So F21 we had found out is 0.285. That leaves that F23 is the same as F13 is equal to 0.715. Now that we have know these values, we can find out these different resistances. So how many resistances are we talking about? This is one resistance. This one is another resistance. This is the third resistance. This is the fourth resistance. And this is the fifth resistance. So what we can do is we can find out each of these values. So 1 minus epsilon 1 divided by epsilon 1 A1. We know the values of each one of them. We can find out that the value comes out to be 8. 1 minus epsilon 2 by epsilon 2 A2, this is equal to 2. And 1 by A1 F12, you know the values of F12, we found out that this is 7.018. And 1 by A1 F13 is 2.797. 1 by A2 F23 is also 2.797. So 1 by F13 is this one. And 1 by F23 is this one, A2 F23 is this one. So these two have the identical values. Now thinking, if you remember how we used to solve problems for our electricity problems, you see that if I consider this to be a node, so this is the node which is there, node J1 out here. At node J1, the sum of the currents is equal to 0. At each node, the sum of the currents is equal to 0. So using that fact, I can write that EB1, let me change the color. Just give me a moment. So what do I have? EB1 minus J1, okay? EB1, we are looking at this part. EB1 minus J1 divided by the resistance, that is 1 minus epsilon 1 by epsilon 1 A1. This is the first term. The second one, which is coming to node 2, is from J2 minus J1. So this is coming from here to here, from here to here. So J2 minus J1 divided by the resistance, that is A1 F12. And the third hand, which is out here, that is J3 minus J1, J3 minus J1 divided by A1 F13. Instead of J3, I can also write it as EB3 because we found out that J3 and EB3 is the same. So that is why I've written it as EB3 instead of writing J3. And this is divided by the resistance, that is A1, 1 by A1 F13. Now we have calculated the values of the resistances. So we put in the values of the resistances, the numerical values out here. Just like we had done it for node J1, we will do it for node J2 also. But let me use another color. So for node J2, this will be a case of EB2 minus J2. It will be EB3 minus J2 and J1 minus J2. So let us start with J1 minus J2 from the left hand side. J1 minus J2 divided by the resistance, that is A1 by A1 F12, plus the second part, that is, or from here we go, here, EB3 minus J2 divided by 1 by A2 F23, and then EB2 minus J2, which is out here, EB2 minus J2 is 1 by epsilon 2 A2. Now we put in the values, numerical values of the resistances, and we get two equations. One equation is like this, and the other equation is like this. Now let us see how many unknowns we have out here. Right here, from the first case, unknown is EB1, J1, J2, EB3. And the second one is J1, J2, EB3, and EB2. So you see that there are 4 unknowns, but we have only 2 equations. So that is not, we cannot solve it. But we also know that EB1 is equal to, sigma into T1 to the power 4. And you know the value of T1 and you know the value of sigma. So you can find out what is the value of EB1. Similarly, EB3 is sigma T3 to the power 4. and EB2 is sigma T2 to the power 4. Since we know the values of T1, T2 and T3, we can put in these values and show that EB1 is sigma T1 to the power 4. This is what is coming out. That is 148.87 kilowatt per meter square. EB2 is 20.24 kilowatt per meter square. And EB3 is 0.4592 kilowatt per meter square. So EB3, if you remember, what is it? It is the third body, which is my wall. Because the temperature of the wall is very small, the amount of energy exerted is also very, very small. Now, if I put in these values of EB1, EB2, and EB3 in these two equations, I am left with only two unknowns, J1 and J2. Then we solve these two equations simultaneously, and we find out that the value of J1 is 33.467 and J2 is 15.054. These two are obtained by simultaneously solving these two equations after putting in the values of EB1, EB2 and EB3. Now, what is the question is that, let us see, is that we are asked to find out the heat lost by plate 1. So how much of heat is lost by plate 1? This is EB1 minus J1 divided by the resistance. So we now know the values of everything. I find out that the heat lost by plate 1 is 14.425 kilowatts. And heat lost by plate 2 is EB2 minus J2 divided by the resistance. So if I put in the values, I get that, sorry, this should have been Q2, my mistake. Q2 is equal to 2.594 kilowatts. And the heat which is received by the room is going to come from J1 minus J3. That means, let me go back and show you. J1 minus J3 and J2 minus J3 divided by their respective resistances. So if you put in the values, this comes out to be 17.020. And you can also see that the summation of Q1 by plus Q2 will be equal to Q3. So heat which is given out by body 1 and body 2 are falling on the walls of the room, and we can find out the value of Q3. So this is how the generalized problem is solved. So any questions about this? Anybody? All right. So when I give you a problem sheet with radiation, I'll try to give you some of these problems so that you know how to solve these using the simultaneous equations. And of course, we will discuss it if you get stuck somewhere. That is not a problem. So this is how we solve the problems when we are using the generalized expressions to find out the net rate of heat transfer between two bodies. Now we talk a little bit about two other small topics. One is heat transfer when surfaces are connected by re-radiating walls. Now, if you look at this figure, you will see, let me just get my pointer again. Okay, now you see out here that this is body 1 and this is body 2. They are parallel to each other, but they are not infinitely long. And hence, whatever radiation goes out of body 1, some of it will fall on body 2, definitely, but some of it might escape from body 2 also and fall outside in the surrounding room or whatever the atmosphere is. So in this case, what happens is that we kind of lose, because whatever is the energy is coming out, unless it falls on body 2, it will not be affected. So some of this heat will be lost out here. So just imagine if I had a furnace like this, where we had two walls where the heat, one wall is coming out and some of the energy is escaping from the top. That is not acceptable. So what we do is that we put some non-conducting refractory brick kind of things on the top and the bottom. And these refractory bricks, which are non-conducting, they are known as re-radiating walls. So what happens is that whatever falls on phase 2 is no problem, but whatever was trying to escape will now hit this re-radiating surface and get reflected back, sort of everything. So a re-radiating surface is one which radiates the entire amount of radiation that it receives from other surfaces. So it doesn't absorb anything. Everything it radiates back. So none of the energy is sort of lost, but it is again reflected back, and now it falls on phase number 2. So this is essentially done to conserve the energy. Now, if two black bodies have areas A1 and A2 connected by refractory, that is non-conducting, but re-radiating walls, a large portion of the radiation from surface 1 is intercepted by surface 2. Now, this view factor is obviously slightly different from the way we had calculated the view factor earlier. And this view factor is essentially equal to my F12. So F12, I've written it with a bar, which is slightly different. So for example, when we consider two surfaces connected by walls of an enclosure. So this is an enclosed surface, just like a furnace. I've given you the example of the most common example is there. And so the top and the bottom are sort of sealed up. So if I want to calculate the F12 bar for such a situation, where these surfaces have got areas of A1 and A2, then this is the expression that we have. That F12 bar is equal to A2 minus A1 F12 square divided by A1 plus A2 minus 2 times A1 F12. So if I know the value of F12, and then I can use that and the areas of A1 and A2 to find out the value of A12 bar. So if I divide it by A2, so this becomes 1 minus A1 by A2, F12 squared, A1 by A2 plus 1 minus 2 times A1 by A2, F12. It is highly possible that A1 and A2 might be equal. If they are equal, this value becomes equal to 1. So this is 1 plus 1 becomes 2, 2 minus 2 times F12. Whatever is the case, if they're of equal area, that is not a problem. We can do that. So as before, A1 F12 over bar is equal to A2 F21 over bar. So what do I have? So if A1 and A2 are the same, then we say F12 over bar is the same as F21 over bar. And if they are not the same and we know the areas of A1 and A2, I can find out the value. So the rate of heat transfer Q is equal to F12 bar A1 sigma T1 to the power 4 minus T2 to the power 4. So F12 is calculated by this expression, and we can put it in the simple case out here because we are talking about black bodies out here. But black bodies they are, but because of the re-radiating surface, it is not just equal to the epsilon is obviously equal to 1, but the values of the view factor are not as we had calculated before. It is a slightly different calculation which is out there. And if we are talking about gray bodies, we take gray bodies into consideration, then what happens is that now we have A1 sigma T1 to the power 4 minus T2 to the power 4, 1 by F12 bar plus 1 by epsilon 1 minus 1 plus A1 by A2 into 1 by epsilon 2 minus 1. Because we have different values of epsilon 1 and epsilon 2 since we are talking about bodies which are gray. And so what I have done out here, I've just written the expression of F12 bar, and then the rest of it is written as is. So if I know the values of F12 and epsilon 1, epsilon 2, T1, T2, I can calculate the Q values provided the areas are known. So this is for re-radiating surface, which are very commonly found in furnaces, where the net rate of heat transfer is primarily by radiation because of the very high temperatures which are involved in furnaces. Now let us look at the last thing that we wanted to talk about, that industrial heat transfer by radiation is almost invariably accompanied by conduction and convection. We just never have only radiation unless, of course, you have the flow of heat through a vacuum. If that is not the case, whenever there is some medium that is involved, we will, along with radiation, we will have a conduction and convection. So if this is the walls of the furnace, you can see here it is being sent by conduction. And then from here, there are two parts. That is, one part is by radiation and one part is by convection. So heat transfer in a furnace occurs mainly by radiation, but a large part of the heat transfer from the flowing combustion gases to the furnace walls or to the tubes of pipes in the furnace occurs by combined conduction, convection, and radiation. There's a combination of this. Heat flows from inside the furnace to the outer surface by conduction. Heat is lost from the outer surface to the surroundings by convection and radiation. So because it is a steady state process, I can say that the net rate of conduction is equal to a summation of convection and radiation. So the temperatures of the inner wall is Ti, the temperature of the outer wall is To, and the ambient temperature is Ta. So for conduction, we can write K by L into Ti minus To. And this is equal to the heat transfer coefficient of convection into To minus Ta plus the emissivity into sigma T0 TO to the power 4 minus Ta to the power 4. Now, because in order to write this as a symmetry, I replace this term epsilon sigma To to the power 4 minus Ta to the power 4 in terms of HR. This is a heat transfer coefficient of radiation. There is nothing like this in reality, but we are talking about it as if there was something like this. So heat transfer coefficient of radiation is essentially equal to epsilon sigma To to the power 4 minus Ta to the power 4 divided by To minus Ta. So if I find out this expression value of HR, this HR can be used out here, and we can write the right hand side as Hc plus HR. That means heat transfer coefficient due to convection and the heat transfer coefficient due to radiation. This multiplied by the temperature difference between the outer wall and the atmosphere. So if you're ever going to do a furnace design, I do not teach you furnace design in this class because it's kind of a little complicated also. But if you want to do that, then what happens is that we can use this as, this is the expression we can use for our calculations. Okay. So that finishes off my section or my chapter on radiation. Since we have a small amount of time, let me just quickly kind of sort of revise where we were and what have the things that we have done. So the first things we have discussed is essentially we have talked about what is radiation. That radiation is an electromagnetic, it's a wave that is given out in that temperature range, which is the whole idea, and the way the radiation behaves is very different from convection and convection. And that is why we study it kind of slightly in a different form. Just give me a moment. Let me go back to the beginning and I'll quickly do a revision of what we have entirely done in the radiation class. Okay, so this is the transfer of heat by electromagnetic radiation. And then we had discussed a little bit about electromagnetic radiation, where in this whole range of electromagnetic radiation does thermal radiation fall, which is what we are involved in when it comes to radiative heat transfer in terms of radiation. Then we talked about the different properties of radiation, where we said that if there is an incident radiation or irradiation, as we had called it in a later class, then we had seen that part of this energy is reflected, part may be transmitted if it is a non-opaque object, and part of it can be absorbed. And the summation of these three are equal to 1 when we are talking about absorptivity, reflectivity, and transmissivity. Then we had talked about the different kinds of reflection, that is specular and diffuse. Specular is exactly the regular kind of reflection that we do. That means the angle of incidence is equal to the angle of reflection. And diffuse is when we have the same angle, but it is in all possible directions. They're reflected in all possible directions. That is known as diffuse reflection. In reality, we said that all surfaces have reflections which are somewhere in between a specular and a diffuse. Then we defined what is a black body, and later on we will also define what is a gray body. Both of these are concepts. They are no real black bodies, but we can talk about this kind of a system where we have a blackened wall, and whatever radiation is coming inside keeps on getting absorbed and reflected till almost everything is absorbed. And that is the closest to a black body that in reality that we can think about. Then we describe the laws of radiation, that is Planck's law. Then we talked about Wien's displacement law, Stephens-Boltzmann law, Kirchhoff's law. Then we came to the concept of view factor, and we had done quite a bit about this view factor because this is a very important part when we try to finally go ahead and calculate the rate of heat transfer between two bodies. Two things are important. One is emissivity and one is view factor. So when we talked about view factor, we defined what a view factor is. Then we talked about simple geometries where we can calculate the view factor. Again, I repeat that GATE examination has got small questions on this view factor because these are quick questions you can do. Then in order to understand and calculate view factors, we learned about different rules. One was the reciprocity rule, one was the summation rule, and then we had other rules such as we talked about the superposition rule, and then we had what else was there? Summation, this symmetry rule, that's correct. All of this we had it. Now the thing is that when we are talking about these situations, we said that those are for simple geometries, and for non-simpler geometries, we saw that Hottel had found out different charts to calculate the view factors, and I had given you examples of only 3 of them. And I'm repeating again that there are other Hottel charts for other geometries. These are the 3 common geometries that we have used in our estimations, calculations, etc. Of course, we have done examples to understand all these concepts of view factors. Then comes the radiation heat transfer between two bodies. First, we considered 2 black bodies and we found out what is the rate of heat transfer between them. And then we talked about 2 gray bodies, which are non-black bodies, and we saw that it becomes a little more complicated. And in all these cases, we have considered transmission to be equal to 0. And for different geometries, we found out what is the way to find out the rate of heat transfer between 2 bodies. And then we talked about radiation shield, how by inserting another plate, which was of the same emissivity as the 2 walls, we can somehow decrease the radiation by half. And this is kind of used in cryogenic industries to reduce the rate of heat loss and maintain the temperatures inside my units. And then we came to rate of heat transfer between non-black bodies. We had done it for parallel plates, but those were not easy things to do. So all geometries will not match up parallel plates or concentric cylinders or spheres. So in order to find out a general expression, we defined what is irradiation, we defined what is radiosity, and tried to solve it like an electrical analog problem. This is the expression for a 2-body system, and this is for which we have reduced it for simpler cases. And when we have a 3-body system, this is the way we can do and solve an electrical analog. That means the sum of the currents at any node or any point becomes same. So we consider this node, we can consider this node, and we can consider this node and find out the values of J1, J2, and J3. Usually what happens, so looking at each of these terms in this 3-body problem, EB1, EB2, and EB3 can be found out if I know the temperatures of the bodies. Epsilon 1s are, that is the emissivities of body 1, body 2, and body 3 need to be known. And if I know the areas, the resistances can be all calculated out. And if I know also, of course, the view factors. The only unknown terms that come out or stand out is J1, J2, and J3. So if I write these, sum of currents at any node is equal to 0, and if I write it for the 3 different nodes, then the 3 unknowns of J1, J2, and J3 can be solved to find out our net rate of heat transfer. And then we talked a little bit about the reradiating walls, and finally about how when we actually have situations, we definitely, unless there's a vacuum involved, especially in the case of industries, radiation is always accompanied by convection and conduction. So that is all that is there about radiation. Give me a little bit of time. By the end of this week, I will send you the problem sheet using the problems of for the problems of radiation. Since we have time now, let us do it very slowly and try to understand each thing that we have. Okay. Any questions with what I have taught today? I have already sent you all the material, so I don't intend to send you anything again. Any questions regarding whatever I have taught? Can someone answer, please?
No, ma'am.
Okay, so if there are no further questions, then I will just stop sharing out here. Okay, and you can always let me know if there are any other questions later on. Let me write it in the group, write to me personally, write it in this